Hi guys. So today and actually the next few days, what we're going to do is really just review some things that we've done so far this year. And the reason for that is you probably noticed a lot of patterns throughout the year, how we've done a lot of the same concepts unit to unit to unit. We've graphed, we've solved, we've found inverses, things like that. But at the end of the year, what's important is not just that we know in that specific unit, how do I graph this type of function, but that we just know how to graph every function, or we know how to solve every type of equation. Because in the future, you're just going to need to know these as steps for future problems. It's not like you're going to be given, okay, now this is your rational unit, now you can graph and memorize your way to graph rationals. You just need to know what the graph is and how to do it. So what we're going to do today is we're just going to review all of our graphs so far from this year. We're going to look at the parent functions, transformations, and just kind of review each of those. So for some of you guys, this might be pretty simple. Hopefully it is. Okay, that's kind of the goal. But if not, it could be just a good review on all the things we've seen so far this year. So when it comes to graphs, we really looked at 9 different parent functions, all right? And the parent functions, it says up here, these were must-knows, okay? Your transformations and parent functions are things you just need to know quickly and easily. So starting with parent functions. Linear parent function, y equals x. That is just your straight diagonal line. Some examples of some points, 0, 0, 1, 1, 2, 2, negative 1, negative 1. All right? Absolute value of x. This is probably the one that most people remember because it's called absolute value and it looks like a V. So there's my absolute value parent function, and I missed a little bit right there. All right, some points on the absolute value function. 0, 0, 1, 1, 2, 2. But instead of negative 1, it's negative 1, positive 1, negative 2, positive 2. Quadratic parent function, y equals x squared. That went through 0, 0, 1, 1, negative 1, 1. But how it was different than absolute value is because it's squared, it would go through 2, 4, and negative 2, positive 4. So it had that parabola shape to it. All right, then after those, look at the cubic parent function. So f of x equals x cubed. That's the one that kind of had that wiggle to it. And we talked about in polynomials because, again, the multiplicity of that 0 was 3. That's why it has that behavior at that point. But let's just list again some of those points. 0, 0, 1, 1, negative 1, negative 1, 2, 8, and negative 2, negative 8. Square root function. This was the first one where we actually had a difference in our reflection over the y-axis. It really actually made an impact on our graph. So square root of x looked like our little one-arm swimmer, I think we called it. Went through 0, 0, 1, 1, 4, 2, and also 9, 3. Doesn't fit on this graph, but that's what it went through. Cube root, we called the two-arm swimmer. Okay, it has kind of the same shape as square root, but again, it continues a little bit further and it has that negative side to it. So again, 0, 0, 1, 1, negative 1, negative 1, 8, 2, and negative 8, negative 2. Again, this is the inverse of cubic, so all those x and y's are just flipped. The rational parent function is the one we did the least with in terms of transformations. We spent a lot of time graphing rationals, but the process was a lot longer. But it is still important that we know our rational parent function. It did have asymptotes. And it had one of those curves up in the top right and one of those curves in the bottom left. Again, we didn't really transform this one that much. We looked at, some shifts and things and how it affected it. But really when it came to rationals, we talked a lot about how to find our asymptotes and our intercepts. So this graph has a vertical asymptote at x equals 0, horizontal asymptote at y equals 0. Exponential and log are also the other two parent functions that have asymptotes. So exponential, again, the base for this one could be anything. All right, so we're just going to say b to the x. So the points that this went through, these are the ones we just did, 0, 1 comma base, negative 1, 1 over the base, and 2 base squared. It also had a horizontal asymptote at y equals 0. And again, that was the shape assuming the base was greater than 1. If the base was less than 1, it was decay and it went that opposite direction. And then the log graph, okay, the one we did most recently, log base b of x, had the vertical asymptote, went through the inverse of these points. 1, 0, base 1, 1 over base negative 1, base squared 2, and again, vertical asymptote at x equals 0. Again, that's the shape assuming that base is greater than 1. All right, so those are the 9 parent functions that we've looked at this year. It's really important that you guys are familiar with the shape of those so you can tell kind of quickly what kind of a graph you have. It's also helpful to know those points because whenever we drew the graph, those are the points that we transformed. Remember, we shifted the origin and then we applied our transformations and reflections to those transformed points. All right, so the next thing we looked at, again, the other really big must-know from this year, which is probably one you guys know pretty well at this point, are your transformations. But just to make sure we review function notation for those. So you've seen this on every time we've done those transformations, but we haven't spent as much time with that function notation, so we need to make sure we're comfortable with that. F of x minus h, that's your shift right. F of x plus h is your shift left. B depended on the value. If it was greater than 1, it was a horizontal compression. If it was between 0 and 1, it was your horizontal stretch. And f of negative x is a reflection over the y. So again, everything that was in the parentheses was horizontal. Algebraically, what we're actually doing to those points, okay, we're changing the x-coordinate in that way. So if I have f of x minus h, I'm taking the x-coordinate and I'm adding h. If I have f of x plus h, I'm taking the x-coordinate and subtracting h. Okay, b times x, I'm taking 1 over b times x, or I'm doing x divided by b. And then f of negative x, I'm making the x-coordinate negative. Anything that happens outside the parentheses, that's your vertical changes. So this was your vertical shift. And if it was plus, it was up. If it was minus, it was down. Multiplied out in front depends on the value. If it's greater than 1, vertical stretch. Between 0 and 1, vertical compression. And a negative on the outside, that's your reflection over the x. So again, all these vertical changes, they affect the y-coordinate. So I would take the y-coordinate and add k, or subtract k, or multiply by a, or make it negative. But again, vertical stuff affects the y, horizontal affects the x. We can have multiple transformations. Remember, we typically like to factor out that b value. Okay, that includes any negatives, because that makes it very clear what your shift is. It kind of puts things in your vertex type form depending on the equation that you have. And it just keeps things a little bit simpler so we don't have to worry about order changing. We can always do our multiplication first and our addition subtraction after. Or we could follow that pattern idea that we've been using all year where we shift the origin and then we just multiply our pattern based off of those reflections, stretches, and compressions. All right, so we're going to do a couple examples. We're going to start with function notation because this is probably the one that we haven't seen as much of most recently. So just remembering, first of all, what that notation means, okay? F of x plus 1 minus 4. The f of x, the x plus 1, it's in the parentheses, that's horizontal. That means I'm going left 1. It means I'm taking my x's and I'm subtracting 1. The minus 4 is shifting this function down 4. So if I'm applying that to this blue graph, I'm just going to take each of those points and shift them left 1 and down 4. And I'll just do that for each point. So with this one, I would go left 1, down 1, 2, 3, 4. Same thing, left 1, down 1, 2, 3, 4. We're just going to go off my graph. left 1, down 1, 2, 3, 4. Left 1, down 1, 2, 3, 4. And left 1, down 1, 2, 3, 4. So the graph that I now have in purple, that's the transformation f of x plus 1 minus 4. Left 1 and down 4. Again, your x and your y are operating independently here. If you have multiple transformations, we'll look at those here in this next section. All right, looking at B. Again, there's one horizontal change, there's one vertical change. The horizontal change affects the x, the vertical change affects the y. So f of negative x, that is a reflection over the y. That's going to affect all of our x coordinates. All of our x coordinates are going to become negative. The 2, it's multiplied on the outside. That's a vertical stretch. So what that means is all of these points are going to get flipped over the y, so we'll do that first. So let's take each of these points and let's just flip it over the y-axis. So negative 2, 1 becomes 2, negative 1. Negative 1, 2 flips over here. 0, 0 stays. 1, negative 1 flips. 2, 2 flips to 2, negative 2. So what I have now in purple, okay, that is just the reflection over the y. Well, what I'm going to go ahead and do now is stretch it. Okay, the order that I do those in doesn't matter because the x and the y operate independently from each other. If you want to stretch it first, go ahead. But again, to stretch this, we're going to multiply the y's by 2. So this first point here is going to get multiplied by 2, so it's going up to 4. Okay, the next point is getting multiplied by 2. Well, 0, 0 still is 0. Okay, taking this point and multiplying it by 2, multiplying the y's by 2, okay, multiplying the y's by 2. And if it's on 0, well, 0 times 2 is still 0. So now, here is my function. Okay, that's my transformed function. Notice the width of this function has not changed. Okay, this total width of this function still is 5 units. Okay, the height, overall height of this unit has changed. So if we look from top to bottom here, the highest point to the lowest point is a height of 8 units. All right, if I look at the original function, there's my highest point, there's the lowest point, that was 4 units. So the overall height of this function has doubled. All right, so now let's go ahead and look at some of these just straight algebraically. We're just going to take a single point and apply these transformations. So I have the point 5, 4. So the transformation, it's 3f of negative x plus 4. So again, x and y are going to operate independently. Let's start with x. F of negative x is a reflection over the y-axis. So instead of 5, this is now negative 5. 3 and 4 are going to affect the y-coordinate. It's a vertical stretch and a shift up. So I would take 4, I would multiply it by 3, and then I would add 4. I'm going to multiply first. So that's going to be 12 plus 4, which is 16. All right, let's look at our next one. 2 times x. Okay, that is a horizontal compression. That means I'm going to take my x's and I'm going to divide them by 2. So my new x coordinate is 5 over 2. Now think about this, okay? Let's say this was just f of 2x, right? F of 2x, all right, is going to give me that 5, 4. So if I take 5 over 2 and I plug that in for x, then it's f of 2 times 5 over 2, which is f of 5. That's the same x coordinate that I originally had. That's why kind of your horizontal stuff's a little bit backwards. All right, then looking at your y coordinate. So we take 4, we're going to reflect it over the x, and we're going to shift it up 5. So negative 4 plus 5 is 1. All right, then the last one. Now, you have 2 different ways for your y coordinate here is pretty easy. Y coordinate is just shifted up 1. That's just 1. F of negative x minus 4. There's 2 ways you could look at this, okay? Again, when we're doing horizontal, we're basically trying to undo this operation and get x by itself. So I could add 4 and then reflect. But what we've been doing all year is we've been factoring out that negative. Because, I don't know why I put an extra x there. Because by doing it that way, we can always multiply first. And we don't have to worry about order based on what we have. We multiply first, we add and subtract second. So by factoring this out, now I can do the negative first. So that becomes negative 5. Negative 5 minus 4 gives me a negative 9. Now let's say I didn't follow that order. I could undo this operation here. I could add 4, and then I could make it negative. So if I took the original, if I took 5 and I added 4 and then I made a negative, I would still get negative 9. I still get that same answer. And again, if I take negative 9 and I plug that back in, negative 9 minus 4 is 5, which was my original. So what this is saying, okay, negative 9, then I'm doing f of 5 plus 1. Well, f of 5 is 4. 4 plus 1 is 5. All right, so the last thing we're going to do is just straight graphing review. All of these are things you have seen so far this year. So again, whatever method you are most comfortable with for graphing, continue to do it. If you like to plug in points, you can still do that. Again, I do recommend you're always aware of the shape of the parent function because that'll help you determine what are good points to plug in so where you can still have a graph that looks like the shape of your parent function. So let's start with quadratics. So what I've been doing all year is I've been shifting our 0, 0 point. And then I've been applying our stretches, compressions, and reflections to that pattern that we know. So for quadratic, all right, this has obviously shifted right 2 and up 1. This is in vertex form, so that's my vertex. The typical pattern for quadratics was 1, 1, 2, 4, 3, 9, and then again, the reflection over the axis of symmetry for all of those points. But again, we had to consider stretches, compressions, and reflections. Well, this graph was compressed by 1/2. So all of those values get divided by 2. So now, again, this is in relation to the vertex. Okay, so from the vertex, from 2, 1, I'm going to go right 1 and up 1/2. I'm going to go right 2 and up 2. And I'm going to go right 3 and up 4.5. Then I'm going to do the same thing on the opposite side of the axis of symmetry to get my parabola. All right, square root. Again, we've gone right 1 and down 3. So it's not a vertex, but our pattern is going to be in relation to 1, negative 3. Well, this is a square root function. So the square root function's pattern was 1, 1, 4, 2, 9, 3. Again, it's the inverse of your quadratic with a restriction on the domain, but we'll review that again later. Keep in mind, if you don't remember these patterns, think about the parent function. The square root of x. Okay, the square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. That's where these numbers are coming from. So then the changes that we need to make, this graph has been reflected over the x-axis and vertically stretched. So all of those second values are getting multiplied. So from that starting point, right 1 down 2, right 4 down 4, and then right 9 down 6 is going to be off my graph. All right, cube root. Again, before we determine that shift, let's factor out that b value. So my 0, 0 point has now shifted right 2 and up 1. So in relation to 2, 1, we'll follow that pattern for the parent function. For a cube root, that was 1, 1, 8, 2, negative 1, negative 1, and negative 8, negative 2. This graph has a horizontal compression, so we're going to divide those x's by 2. So So from 2, 1, again, right a half, up 1, right 4, up 2. Left a half, down 1. Whoops. And left 4, down 2. And then finally, absolute value. Okay, so absolute value, again, this has shifted left 1. That's where your vertex is. Has not gone up and down at all. And then remember, for absolute value is actually a little bit easier. We didn't really worry about that pattern because really that 3/5, it's really your slope off of that vertex. So 3/5, I'm going up 3 and over 5. And I'm going up 3 and left 5. That's really the easiest way to do absolute value. Now, if you want to do that pattern, you're more than welcome to. Okay, I can do 1, 1 and 2, 2, and I can multiply those by 3/5. But it's a lot easier to get some nice, pretty points if we just say, hey, that 3/5 is my slope. All right, and then the last ones we did were the two that actually were not parent function transformations. So 2 different graphs we looked at this year that we modeled a little bit differently. So the first one was polynomials. So while x cubed did have transformations and we did apply those, for polynomials we didn't. It had a different process for how we graphed it. So if you remember, the first thing that we did was we found the zeros. All right, we found the x-intercepts. So this graph has 3 x-intercepts. So 0, 4, and -5. Then what we did was we talked about the multiplicity of those zeros. And what that meant was, what's the exponent on that 0? Then what we did was we determined, what does that multiplicity actually mean? Well, if the multiplicity was 1, it meant my graph would cross through that point at 0. If the multiplicity was even, it meant that graph would touch or bounce or be tangent at that point. If the multiplicity was an odd number greater than 1, it still crossed. But as it crossed, if you remembered, it didn't straight cross. It kind of wiggled or bent a little bit as it went through. Again, very similar to what x cubed does. How it doesn't just go through that point, it kind of bends as it goes closer to it. Then the last thing we looked at, well, sometimes we did this first actually, was end behavior. And end behavior helped us to determine what the ends of this graph looked like. So we looked at the degree and the leading coefficient. So the leading coefficient, we cared if it was positive or negative. Well, if I look in front of all of my x's, in front of all my x's is positive. So this is a positive leading coefficient. The degree, it depended on what form this was written. So if this is written in standard form, my degree is just the biggest exponent. If it's in factored form, though, we need to consider, if I FOILed all this out, what would be the biggest exponent for my x? Well, I've got x to the first, x squared, and x to the third. So I would basically add all those exponents up and get a degree of 6. So that we said was an even number and a positive leading coefficient. Positive and even looks like y equals x squared, where both ends are going up. Then we just continued our graph from here. So we'll follow our pattern here. So at -5, that graph is going to wiggle because of the exponent at that point. So it's going to, I probably should have made that arrow a little bit better. Wiggle as it goes through. Then the next 0 that we're going to approach is 0. At 0, my graph crossed. So I'm going to cross through that point. Then the last intercept is 4. At 4, it says my graph is going to touch. So I'm going to touch that point and then go back, and it matches the end behavior we talked about. Now, the other thing we said is the height of those points, it does not matter if you do not have a calculator. Typically, I didn't even give you grids like this. I typically just gave you the x and the y axis because of that reason. So don't stress about the heights of those points. They are not accurate on my graph. You really would need a calculator or calculus to really get those exact. All right, so the last kind of graph that we looked at was rational. And again, we talked about this. We didn't really do parent function transformations for rationals. Rationals, we had that way longer process, and it was finding all those components. So we had vertical asymptote, horizontal asymptote, x-intercept, and y-intercept. Vertical asymptotes occur because we can't divide by 0. So to find a vertical asymptote, we set the bottom equal to 0. Horizontal asymptote, we look at the degree of the top and the degree of the bottom. Okay, these were same degree, you divide the leading coefficients. X-intercept, it happens because it's 0 divided by a number. Okay, we're solving for when it equals 0, so we set the top equal to 0. And then y-intercept, I plugged in 0 for my x's. And that is my intercepts. To get the last curve in this graph, we used a couple different methods. One of them, again, we talked about tangency and together. Since there's no squared factors, we know that this graph has to go in the opposite direction at the asymptote. I also know I can't create x-intercepts that don't exist. So I can't put anything in that box because it's not going to create something down there. All right, so that's it. So a little bit of a longer video, but again, really just all review. Nothing in there there's nothing in there you haven't seen at some point this year. It's really just kind of combining it all together. So there are a few practice problems that you're going to do for a completion grade. The check, though, for today is actually a little bit different. The check is going to be a Desmos activity. And I mentioned this on the Desmos, but some of these questions are going to be incredibly easy when you have a calculator and you have notes, and I'm aware of that. Keep in mind, the reason we're doing this is to make these skills easier for you for your future math classes. The better you know these, the better it's going to make things for you in your future math classes when you don't necessarily have a calculator to be able to graph these. And I didn't mean to go to that slide. Again, if you have questions, you can email me, you can fill out a video request, or you can join that Zoom tutorial session.